What is going on here? I clearly picked the best day to do this recording after jiu-jitsu last night. So in today's video, I really want to talk about the best way to really summarize and understand linear algebra as a whole. I'm not going to claim to teach you all of the stuff you need to know about linear algebra, but this approach, which I'm hoping to extend in future videos, is, in my opinion, the best way to learn it, and in particular, the best way to teach it. I've taught this at both the University of Sydney and the Australian National University at great length, and students have very much appreciated this style of teaching linear algebra and this style of, in particular, teaching eigenvalues and eigenvectors. Any course in linear algebra has a lot of stuff going on. We learn about eigenvalues, eigenvectors, change of basis matrices, linear maps, row reductions, all this nonsense. And it's common for students at the end of the course to have no idea how anything fits together. You have a lot of vague ideas and these stupid calculations you learn how to do, which seem meaningless. And then you hear all these mathematicians or older university students in higher years or postgraduates saying that linear algebra is the most important thing you're ever going to learn. And you're like, this makes no sense. These concepts are so abstract, they're meaningless. Why does anyone care if I can calculate the determinant of a 2x2 matrix? What does that have to do with anything? The purpose of these videos, these quiz-style true or false videos, is to show how everything is linked together in a unified framework. Now, I could personally just tell you and give an exposition on how everything fits together. But in my opinion, the best way to do it is actually get your hands into it and test whether you can actually answer, is every invertible matrix a change of basis matrix? What's the difference? What is a basis? You really have to address these questions when you answer true or false problems, right? You'll have to really think, do I know what these concepts mean? And in the course of it, you'll be surprised at how unified all these ideas are. So let's look at this first question. We want to know whether a diagonalizable matrix is invertible. So before we get into it, take a moment to see if you can prove the statement, or if you don't believe it's true, you believe it's false, try to find a counterexample. So recall that a matrix A is invertible if there's a matrix B such that AB is equal to BA is equal to the identity. In other words, we can undo the operation of matrix multiplication via another matrix. An equivalent way of defining this is by saying that a matrix is invertible if its determinant is non-zero. Again, to make sure we know what we're talking about, take a moment and see if you can write down an example of a 2x2 invertible matrix as well as a 2x2 non-invertible matrix. My example of an invertible 2x2 matrix is just the identity with 1, 0, 0, 1. My example of a non-invertible 2x2 matrix is just the zero matrix, the matrix with zeros in all columns and all rows. In the comment section down below, let me know what examples you chose. Did you choose the dumb ones that I chose, or did you choose more interesting ones? Now, a matrix A is said to be diagonalizable if we can find a basis such that A is diagonal with respect to that basis. Put in another way, we can find an invertible matrix P and a diagonal matrix D such that A can be written as P, D, P inverse. This is exactly the same as saying that we can change the basis such that when A is written in this basis, it's diagonal. Again, to make sure we're on the same page, take a moment to write down an example of a diagonalizable matrix. The example I'm going to choose is again the dumb one. I'm just going to choose the identity matrix with 1s on the diagonal and 0 elsewhere. This is certainly a diagonalizable matrix. It's diagonal. So the relationship between invertibility and eigenvalues is seen from the fact that the determinant is given by the product of the eigenvalues. So if the eigenvalues are lambda 1 through lambda n, then the determinant is just given by lambda 1 times lambda 2 all the way through to lambda n. Now a matrix is not invertible as soon as the determinant is 0. And so in particular, a matrix is not invertible as soon as one of the eigenvalues is 0. So as a consequence, all we need to do is find a diagonal matrix with at least one of the diagonal entries being 0. The simplest example, perhaps one of the simplest examples, is given by the matrix 1, 0, 0, 0. This is certainly diagonal. All the entries that are not on the diagonal are 0, but it's not invertible since there's a 0 on the main diagonal. Okay, let's look at our second true or false question. If A is similar to a diagonalizable matrix, then A is diagonalizable. Again, take a moment to see if you can prove the statement on your own, or find a counterexample. So recall that two matrices A and B are said to be similar if there's an invertible matrix P such that A is equal to P inverse BP. As an additional fun question, see how this is expressed in terms of bases. What I mean by this is, what does A equal P inverse BP mean in terms of what you know regarding bases and change of basis matrices and so on? Now what I mean by this is that two matrices are similar if they are the same matrix, just represented in different bases. I remember when I was an undergraduate, this was so enlightening, this one sentence here. It took me so long to realize exactly what a change of basis matrix was, what similar matrices were, and what all this eigenvalue nonsense was about. Now, an invertible matrix as well, that's just a change of basis matrix. So two matrices are similar if they differ only by a choice of grid. And that's exactly what a choice of basis is. When you write a matrix down, what allows you to write it down is the fact that you've chosen a grid. So these linear maps and these abstract ideas that we learnt in linear algebra, those are made concrete when we fix a basis, fix a grid, and then when we write the linear map down with respect to this grid, that's what a matrix is. An invertible matrix is when you just change the grid, and two matrices are similar if they are the same matrix, as long as you can get to one to the other by just changing the grid. Okay, so if B is some diagonalizable matrix, we know that there's an invertible matrix T and a diagonal matrix D such that B equals T inverse dt. In other words, B can be written as a diagonal matrix if we change the basis of our vector space. Or in other words, if we just change the grid, we can get B to be written as a diagonal matrix. In particular, if A and B are similar, then I can write A as P inverse BP, using the fact that B is diagonalizable with B equal to T inverse dt. We can write that A is equal to P inverse T inverse dTP. But since the inverse of TP is P inverse T inverse, so when you invert the product of two matrices, right, you have to flip the order. So in particular, we can see that A is equal to TP inverse dTP. But now TP is an invertible matrix. You take the product of two invertible matrices, you get an invertible matrix. So in other words, if A is similar to a diagonalizable matrix, it has to be diagonalizable. Okay, last question, true or false? Two matrices with the same eigenvalues are similar. Since we've covered all the material required to address this question, take a moment to see if you can give either a proof of the result, or if you don't believe it, construct a counterexample. Okay, so do we think the result is true or false? Well, let's consider the matrices A and B given here. So A is the matrix with ones along the diagonal, 0 elsewhere. And B is the matrix with ones everywhere except for the second row, first column, which will have 0 in that entry. So you can convince yourself that the eigenvalues of A and B are both equal to 1. And they occur with a multiplicity of 2, so 1 occurs twice. And what we need to do now is check if there's an invertible matrix T such that B equals T inverse AT. In other words, we need to check if we can change the grid such that A can be written as B or B can be written as A. Now, since A is the identity matrix, we see that T inverse AT is just T inverse T, because AT is just going to be T again. But now T inverse T, well, that's the identity by definition. So we see that T inverse AT is exactly the identity matrix. So in other words, if a matrix is similar to the identity, it has to be the identity matrix itself. But notice that B is not the identity matrix, right? B has this 1 in the top right-hand corner. So A and B can't be similar, even though they have the same eigenvalues.